We're going to start second of LatinCom this Thursday. And part of the program, we have a tutorial called on simulating direct to satellite IoT networks with OMNeT and Florez. Uh, Today, let me introduce you to the presenter, which is Alexander Choquenaira Florez. Please welcome him with a big applause to start. Thank you. All yours.
Thank you. Good day to everyone. My name is Alexander Choquenaira Florez, and today I will make the presentation of this tutorial session that has the name of a tutorial on simulating the satellite IoT network with OMNeT and FLoRaSat. Basically, in this tutorial, we will make an introduction on OMNeT, on FLoRaSat, how is the process of installation, the process of customization, the configuration of some documents, some files, some parameters, and everything. It will be very didactic, so I will share in some point. First, I will make an introduction of several concepts. Then I will make a presentation of even the installation of OMNeT, of the simulator, how it's configured, the steps necessary to configure the simulator. First, let me talk about the steps of this tutorial. What is me, Alexander? I'm a PhD student on my second year. I'm doing my PhD in Lyon, in France, and here I have some problems with my laptop today with a microphone. So that's the reason why I'm using the tablet as a microphone. So my supervisor and my partner can present for the presentation. Maybe Juan, you can start to present yourself.
Yes, happily. Thank you, Alex. Hello, everyone over there on the room. Thank you for joining the FLoRaSat tutorial. So my name is Juan Fraire. I am an IEEE researcher in France, in Lyon. Since many years, we had been studying the problems of protocols for satellite networks. Specifically, in this session, we're going to focus in IoT, Internet of Things protocols adapted to the satellite context, specifically as Alexander will present a family that is known as direct-to-satellite IoT, and to analyze and to make performance evaluation of these systems, we have developed FLoRaSat, which is the simulator that you will enjoy and learn about today. It's a collaborative effort between Alex, Benoit, and some other researchers that are using it. So I really hope you enjoy the tutorial and that we are fully open to receive questions and also find students that are interested in collaborating and using the simulator. We are just building a small community around it, and you will be more than welcome to join, and anything that we can help you with, we are here for that. So I really wish you enjoy the tutorial. I will be online as much as possible. I am currently at the IATF meeting in Montreal, so we might disconnect eventually. But Benoit and Alexander will be here. Benoit remotely and Alexander on site will be here, sharing with you the details of these interesting simulators we have at hand. So with that, I wish you the best of experience, and I pass the talking to you, Benoit, if you want to present yourself briefly.
Yeah, hello to everyone. I'm Benoit. I'm now a PhD student, also in Lyon, but also with this company called Kineis in France. I've been working on FLoRaSat for many months now, and I'm the main maintainer of the tool with Alex. So I will be happy to answer all the questions and to provide some insight on the tool. So I hope it will be a good session for everyone.
Great. Thank you, Benoit. Thank you, Juan. I will continue with the presentation. Following. Sorry, okay. The table of contents that we will talk about in the presentation is first the introduction, where we basically present some concepts, present some terminology that we will use in this tutorial session, and more specifically that we will use in FLoRaSat or any kind of DTS IoT application. After that, we will give some detail about these concepts that are required for this kind of application. Then we will talk about, we will give an introduction of OMNeT++, which is the IDE, the simulator that we use to create FLoRaSat. After that, we will present the FLoRaSat per se. We basically will make an overview of the tool, the installation process, and we will detail some architecture. We will detail the architecture of FLoRaSat. After that, we will present a tutorial based in two perspectives. I mean, we will have an approach which is more focused for user. Basically, in this approach, we will set some parameters and we will test the network as without touch code or something like that. And then after that, we will present another another point of view, more oriented for developers. So in that part, we will talk in detail about how is OMNeT and FLoRaSat works, and based on that, we will provide some examples of execution. We will provide some details about the implementation of FLoRaSat, about the version of FLoRaSat, about the modules that we have in FLoRaSat. And to finish this presentation, we will talk about some conclusion, we will detail some future work, and of course, there will be some questions and answers that are required. Please feel free to raise your hand or interrupt me if you have any question. So we have 3 hours, so I think that we will have enough time to discuss about it. Okay. In the first topic is about introduction. Well, as we know in the previous presentation, in recent years, there was a significant increase in the number of space projects. It's basically the main reason of this is that now there is a new kind of satellite, a new kind of launches exist that basically they have the name of nano satellite, and we also call it CubeSat. These kind of satellites are very cheap, very easy to deploy, and also they have very small. It's not the traditional satellite image that we have in our mind, a big thing in the space. No, this is very small, and due to this, this kind of satellites can, of course, have the potential to work as a mobile gateway to support a connection between an IoT device and to the satellite. This connection can be in 2 ways. I mean, it can be a direct connection, which means the connection from the IoT device to the satellite. And also there is the possibility to have an indirect connection, which implies the use of a gateway. So basically the device connects to the gateway, and then the gateway connects to the satellite. And of course, satellite IoT emerged as a combination of satellite communications with the Internet of Things, IoT. This new field, this field that is a combination of both, of course, attract the interest of IoT community because they are always looking for new applications, and of course, considering that now you are working with satellites, you have more coverage. You don't have you can reach other regions where in other ways it was impossible to reach. So of course, this combination needs to address several challenging issues. For example, we have the connectivity. Since we're gonna work with satellites, and of course the satellite moves around the planet, around the Earth, and there will be some cases, depending on the application, where the satellite will move, and maybe the device won't have a connection to the satellite. And also, another big problem that needs to be addressed in satellite IoT is the problem of lag. For example, we have I mean, the distance between the device and the satellite is big. And this, of course, introduces some latency problems that needs to be addressed for this kind of applications. However, if we overcome this challenge, of course, there is a big opportunity to control, to monitor, collect, and analyze big quantity of data. This is a big opportunity for new kind of application. Following, well, in this context, of course, the simulation tools performs a critical role in this kind of scenarios, especially because, for example, it's really hard to have access to this kind of data. It's really hard to, even if now it's more easy to deploy satellites like the CubeSat, it's really hard to make a real experimentation in that. And for that, it's something that increase the importance of simulation tools. For this tutorial, we introduce FLoRaSat. FLoRaSat is an open source, event-driven end-to-end simulator tool that basically is designed for this kind of application. Well, we demonstrated that we presented FLoRaSat in some papers, and additionally, based on that, we keep working on FLoRaSat. We added some modules, and we presented another paper with the new version of FLoRaSat. And well, basically, using this paper, we validate the importance of FLoRaSat, so we were able to study and analyze the performance of networks. Well, the technologies and software that they are involved in FLoRaSat, basically, what FLoRaSat is designed to work with LoRa, which, as we know, is a long-range, low-power communication for IoT device. And additionally, we will talk about some LEO constellations, because it's the main kind of satellite that we use in IoT applications. And after that, we will talk about some MAC and some routing algorithms that are necessary to work well in a LEO constellation of satellites. Another another software that is involved in this tutorial is basically OMNeT++, which is the main tool that we use for the development of FLoRaSat. And well, OMNeT is a modular C++-based discrete event, which is widely used for modeling communication networks. And then we also use INET, which is an open source framework designed to work in OMNeT++. Basically, it supports the wireless and mobile network connection. Additionally, we will also work with FLoRa. FLoRa basically is a framework that was designed for OMNeT++ that basically stimulates and implements the LoRa network characteristic feature. So, and it was implemented in OMNeT++. And of course, FLoRa use INET, the framework INET. And well, since we use OMNeT, which is basically use C++, so that's why we will use some C++ code. And additionally, for the processing of data or the results of our simulator, maybe it would be necessary also use some Python to create some graphs, apply any other kind of analysis, and so on. Well, now please let me talk about some concepts that we will use in this tutorial. First, the first concept is important to know is the satellite IoT. As I described before, satellite IoT is basically the combination of satellite communication with Internet of Things, with IoT. Well, basically, satellite IoT take advantage of the satellite, so we can create new IoT applications that have a global coverage to reach device in less accessible regions. For example, I don't know, in the sea, in the desert, or something like that. using these kind of scenarios, it's not feasible the implementation of a terrestrial gateway. So for this, for example, we can use satellite IoT because the device will connect directly to the satellite. And of course, this new field attracts the interest of IoT community because they are always looking new kind of applications and new kind of solutions. And with this potential is something that attracts more interest for the research community, for the enterprises, and so on. However, for satellite IoT, we need to, for example, address some critical IoT limitation. Sorry, satellite IoT address some critical IoT limitation. What I mean is that, for example, we usually have this limitation, the coverage limitation. With satellite IoT, you will have a connection, always a connection with the satellite. Additionally, you will have some reliability and resilience because the device could connect with the satellite anytime it's necessary, and of course, it will provide the processing, the management of big quantities of data, specifically in the sense of the devices and so on. Okay, basically in satellite IoT, we use two kinds of orbits, with two kinds of satellites that we call. The most common and the most traditional image of satellites that we have is the geo satellites. That they have this big satellite that is around the air and it covers a big quantity, a big area, a large area. So for this, the geo satellite, they fly at a high altitude, or more than 56 kilometers, and they move very slow. So they have a global, a large area coverage, and they start to move around the earth at a low velocity. And in the other hand, we have another kind of satellite, which basically is called LEO, which they fly, they orbit on a very low altitude, lower than 1,000 kilometers, and they move very fast. They move very fast around the earth. So the problem with LEO is, of course, that they reduce the latency if you compare with GEO because it's more far away, but the LEO is more close. So the application that use LEO satellites, they have a lower latency. However, they also need to address, since the LEO satellites move very fast, there are some problems that needs to be addressed. For example, some problems that need to be addressed to have a global coverage and a continuous connectivity. Is necessary the deployment of several LEO satellites in order to create a constellation. So, for example, in the image, we can see that there are several LEO satellites, and we can create a constellation with them, and they will move around the earth in order to have a global coverage, and so we will have a continuous connectivity for the IoT device. Okay. Following, based on this kind of orbit, and more specifically in LEO satellite, we have two kinds of satellite IoT applications. Basically, there are two deployment cases for satellite IoT, and this is what we call a stereo architecture. Basically, there are, as I mentioned before, we have the direct connection between the IoT device and the satellite, and that's something that we call direct to satellite IoT. And we also have this indirect connection that we call indirect to satellite IoT, which implies the connection of the IoT device with the terrestrial gateway, and then the terrestrial gateway will connect to the satellite. And well, as we can see in the image, this is basically the kind of the taxonomy of this kind of application. Well, in this tutorial session, we will especially focus on direct satellite IoT, DTS IoT. Well, as I mentioned before, in direct to satellite IoT is the connection is direct between the IoT and the satellite. And for this, the main feature of DTS IoT is that it's not necessary any terrestrial infrastructure, any terrestrial gateway. It's not necessary. And of course, it needs to use LP1, low power connections. Technologies like can be, for example, LoRa and NB-IoT. For this tutorial, we would specifically focus on LoRa. And well, the application of that we can, the application of DTS IoT, it covers several kind of fields. For example, we have with DTS IoT, we could create some applications that are focused on the environment monitoring, some also the global tracking, smart agriculture, maritime service, and between any kind of between all alternatives. And well, the main challenge that we need to address in this in DTS IoT is basically the power of the devices. Of course, these kind of devices they don't have a lot of power, and also the intermittent visibility of the satellite. Since the connection is direct between the IoT and the satellite, and the satellite is moving, there will be some cases where the satellite will not be able to receive any message from the device. And of course, there are several companies, there are several main actors that are working on this kind of application. For example, in the image, we can highlight some of them. We have Choquenaira, we have Lacuna, we have Y, we have FLoRaSat. That each of them has his own satellite, each of them has his own protocol, but basically they support, they provide this kind of application, this DTS IoT application. Okay. The other big thing that we will cover in this tutorial is about OMNeT. For example, OMNeT is an event driven simulator. Well, basically, OMNeT, as we can see in the image, is a simple flow diagram that presents how this kind of simulator that are based on events work. Basically, we have an start point. We have an initialization step where all the parameters are set, all the modules of the simulator are set and be ready to start. Then we have this wait window where basically the simulator wait for a new event, for the next event. After that, there is this function that basically handle the event. They do the necessary steps, and then the process continues, and it determines if the simulation finished or not. If not, so it starts again, and the process continues until the end of the simulation. For example, this kind of simulators are based on different events. For example, an event can represent a packet transmission, an event can represent the reception of the transmission, an event can represent the reception, the pre-process of the reception of the package, the transmission, the retransmission, the transmission to other satellites, all these kind of events, events. And of course, the best thing of this kind of simulator is that they support a large network of systems. In this kind of simulator, we have, for example, OMNeT++, which is the simulator that we use in this tutorial. And also we have another big famous simulator is NS3. And also we have NB, which are very famous simulator, event-driven simulators. Well, now I will talk about OMNeT++. Basically, OMNeT++ is a modular discrete event-driven simulator, which is used for create or build big networks and big communication system models. A good thing of FLoRaSat, sorry, about OMNeT is that there is a big community that is always giving support, and new versions is always in updating the simulator, the OMNeT. And well, this is something good because when there is, it is not a best tool, but they have several, they have a big community that supports the use of OMNeT++. Well, in OMNeT++, we have three types of files, basically. The first one is the net file, where basically you can create the modules that will part of the network, and also in the net file you create the connection of this module. You can create the communication between them. You can create sub modules inside another module, and of course there are some parameters that are required. These parameters are set in the ini file. Okay, so for example, you have an ini file that you can say, okay, I want that this parameter in this running, I want that this parameter has this value. So in that way, you use the ini files to set the parameters that are used in the net file. However, this is only the process of create a network. This is only the process of establish the parameters. But you need another file to establish the logic of this module. And for that, we use C++ file, which basically you have the H file and the CC file, where you can specify that this file corresponds to this module. And this module, okay, in this module, you have all these parameters that are set in the ini file. And in the C++ file, you develop the logic of this module, how they manage the data, how they process the data, how they transmit the data to another module if it is necessary. Another big thing of OMNeT++ is that it was developed in a modular structure. So this is good because we can represent each module. For example, a device can be represented with a module. A satellite can be represented with a module. A gateway can be represented with a module. A ground station can be represented with a module. So based on that, this is a good feature of FLoRaSat to this modular structure. Additionally, OMNeT++ supports the introduction of external tools. For example, another framework, like I mentioned before, and I will detail later, like Ylnner framework, like FLoRa framework, and any kind of module. There are several modules that focus on OMNeT++. So, with this in mind, emerged the question: why to use it? Why to use Why to use OMNeT++ for DTS IoT? Basically, with OMNeT++, we were able to manage large scale simulations, big networks, without a lot of without the necessity of a powerful computer. You don't have a lot of resources to run a simulation. You don't need the super server where you can run your simulation. It's not necessary. And of course, another big feature of this is that OMNeT++ supports the integration of external frameworks like INET and FLoRa, and this is important tools that we use in the development of our simulator of FLoRa. So now, since I mentioned it before, INET framework basically this framework supplies the core component such as the interfaces, the channel models, the wireless networks, the mobility components. So it's necessary it's a big framework used for OMNeT++, and it's necessary it was necessary for the development of FLoRa. Additionally, we also have FLoRa. As I mentioned before, basically it's an open source LoRa-based simulator that was developed in OMNeT++ and using IEEE. So with that in mind, basically we adapt FLoRa and we make some changes and adapt them to be able to establish this DTS IoT application, this DTS IoT networks. And this is the result of, and FLoraSat is the result of the combination of all these concepts, all these technologies, all these software, and FLoraSat, which is an open private open source end-to-end simulation tools that use OMNeT++, as I mentioned before, C++, and other kind of technologies. And this is what FLoraSat was designed specifically for DTS IoT application. I will make also a presentation of the installation of OMNeT++, but I don't know if you have any questions, so in any case, I can continue with the presentation. No, not go. I mean, it depends of the network, of the size of your network. But for if you try to simulate a Starlink constellation, it will be require more resource. But in general, it's not necessary to have a lot of a big computer. It's only with a regular one you can simulate. Sorry. Okay. Well, for example, yeah. I will run the simulation in my laptop. I will run everything, and also in the paper that we introduced, that we presented before. Basically, the majority of simulation were made on my personal laptop, so it's not necessary a big computer. So, so with a personal laptop, it's enough to run. Well, yeah. Well, you can. I put this QR code. In this QR code, you will find any information that you require for the installation, the official links, the commands, and even in that file, in that folder, there is, for example, previously I was using a Mac to run FLoraSat, and it's kind of difficult to even install OMNeT++. It's kind of difficult. But installed in this new generation of Mac laptops is more difficult because they use this ARM processor, so it's a mess install OMNeT++ in a Mac. So, for example, if you have a Mac, what I can recommend is use a Docker to run a Linux. So that's what I used to do because it's the best way that I found. I also put an image of the Docker image to download. So basically, you can import that image directly to your Docker installation. I suppose that we will work only also if you have any other system operative that if you use Docker, right? Well, you can use that, and if you are using Windows, I recommend to you basically use WSL to run Linux on Ubuntu system, and to start with the process. Well, that's basically. I also put the Wi-Fi and the path to if you want to participate in the process of installation. Well, basically, the main steps, I will give some detail about the main steps of the installation. For this tutorial, I used the version 603, but I think that last version is the 6.5. I don't know exactly. I suppose that there won't be any problem if you use a new version. But basically, for this tutorial system, for the moment that I installed it, I didn't update it, so that's the reason why I'm still using this version of FLoraSat. But basically, you need to download and unpack the, the file. Then you need to, well, it's basically the steps that are in the official guide of installation, in the official installation guide. But if you want to try and if you are having any problem, I can help you to solve it. But basically, we will give some details about this installation process. You need to create an environment, and then you need to install the prerequisite package. Basically, it's just a copy paste of these commands. I just put it also in the file that I shared with you before. And after that, you need to install some Python package. Always, you need to be in this environment that you created before, EM environment, and then you install well, you install all the Python packages required for OMNeT++. This is only for OMNeT++. It's a mess. It's really complicated to install OMNeT++, but when you have the correct step, it's kind of easy. Then you need to configure and build the project, which basically is follow these commands. Well, things additionally, for example, if you will install OMNeT++ in a Mac or with Docker, as I used to do it. For example, what I made, it was just to create a Docker, a container with the image that I shared with you in the link, and to open the IDE, it was necessary to use another tool that is called Quartz, which basically allows you to open an IDE directly without the installation of the IDE of the operating system. So it's kind of easy. The only thing that you need to do is open Xquart in your Mac or in your laptop, run terminal that will allow to the migration of the IDE to open it in your local system, and then you need to run the Docker and just follow the previous steps. But however, what I in the link that I shared with you, there is in the QR code it opens a file where there are several links, several commands, and you can find also the link to download the image with the OMNeT++ installed. So it's more easy for you if you want to take a chance, if you want to give a chance to OMNeT++. Well, there are some errors that along the time that we use OMNeT++ that we found. But the most common error that I found is that at the moment to compile the project, there appears this error. Basically, the thing that I need to do is modify this file and change the value of that variable to no, so it will the OMNeT++ will compile without any problem. Okay, so with this. We cover the installation of OMNeT++, and again, if you want to try and install it, you can just send me a message, and I will be happy to help you in the installation of OMNeT++. Now, since we already have OMNeT++, we need to download Florez and configure it to be able to use it. Okay. Just a quick reminder about FLoRaSat. As I mentioned before, it's an open source event driver end-to-end simulation tool that was developed using OMNeT++. FLoRaSat, in the beginning, it was a simulator very small with a low number of modules, but a lot of time we worked very hard to improve his feature, to improve the number of modules, and of course this create we needed to improve the architecture, and so in that way we can increase the simulation capability that FLoRaSat has. For example, we had some some months ago, we presented a paper that introduced the new version of FLoRaSat V2, which basically has new modules, like, for example, a constellation creator that basically is a module that helps you to create a constellation of satellites along some parameters that you set in the INI5, and another modules that can be, for example, the devices, the topology control that helps you to manage how the satellites are moving and manage to establish and continue updating the connection between them, between the satellites and between the satellites and the ground station and so on. But in that point, we noticed that FLoRaSat was, each time was bigger and bigger and bigger. And since in this project worked several people, so it was obvious that they work and they move to another project, and the process, the architecture of FLoRaSat changed, and it's a mess. It increased a lot that now it's impossible to. It's really hard to start to work on that. It's really hard to understand how it's worked, how it works. For that reason, we decided we need to make a break, and we need to make a new architecture of FLoRaSat that we call V3 Edu, which is now it's under development. But in this architecture, everything is structured, it's more intuitive, it's more practice for educational purpose, because it's more easy to find. Okay, this is for the physical layer. So it's more easy to find which file to set. It's a new architecture that we are working, and we will present today. And this architecture is more easy and more intuitive, start to work in Florez. Okay, now I will make a comparison of FLoRaSat. Since I detailed before, this is the importance of this kind of tool, of simulation tools focused on DTS IoT. However, for example, when we make a literary review of alternative tools that we found, we especially focus on four main aspects. If they support an orbital propagator, if they support a packet simulation, if they are designed for DTS IoT, which basically is the field that we are focused, and if they support the constellation grain. And we found several alternatives. Some of them are open source, some of them are not open source. But until our knowledge, FLoRaSat was the only simulator tool that was able to satisfy all these features that we focus. So this highlights again the importance of FLoRaSat. This highlights again how is the benefit of start to work on FLoRaSat if we compare with another alternative. Okay, this was the architecture that we had for FLoRaSat in the version 2, in the previous version. Basically, this is the extended architecture that we developed, and we introduced a new module. Here, for example, we're going to create boxes. They represent the original modules that were introduced in the first version of FLoRaSat. And the orange, pink, the orange boxes, they represent the new modules that we introduced for that version of FLoRaSat, the V2. Basically, in that moment, we introduced four main new modules. That is the constellation, the event manager, the topology, the routing, and the statistics module that allows you to create some graphics and evaluate the performance of some routing algorithm. For that version, we highlight the four new modules. And for example, we have the topology control, the constellation creator module. Basically, this module supports the creation of a new constellation of satellites, and of course, it supports a Walker Delta and a Walker notation for the constellation creator. And using this constellation creator module, we were able to create complex and big constellations like OneWeb and even Starlink with thousands of satellites. Well, the positions of this constellation were validated against some values that we took from another popular simulator, SDK, and we noticed that there is no, if we use our constellation creator, there is no difference. There is no significant difference between in the positions of the satellite. Well, another big model that was introduced in this new version is the topology control. Well, basically, this model manages the communication between the satellite and the ground modules. This means that basically it keeps updating the ISL, which is the connection between satellites, inter-satellite links, and also the GSL, the ground satellite links. This model basically connections of the satellites, since they are moving, they will be necessary to update it. We also have another model, which is the event manager model. And this model basically activate or deactivate the ISL connection. And this is important because with this model, we can test the routing algorithms that we can create and implement on FLoRaSat. And we can see how this algorithm works in the case of a failure, in the case of a congestion, and so on. Another big model that we have here is the FLoRaSat C. Basically, in this model, it's a command line that was used, that was developed using Python. And in this model, we can create some graphs, we can create some metrics to compare the performance of some routing algorithms that are used in the constellation. And of course, it supports an easy integration of new graphs or new metrics. Okay, so now I will talk about, we will present some use cases of FLoRaSat. As I mentioned before, we will have 2 points of view of this tutorial. The first point of view will be focused on only users that want to use run a simple simulation, see how understand how set the variables, how to set the parameters, and for this first point of view, we will use the FLoRaSat V2. Basically, because it's the version that supports that has more modules, that it has more functionality. So I think it would be best. It would be better if we use this version for this kind of point of view. And additionally, in the other point of view, we will be focused on the developer user. For example, if someone of you want to start to work or create a new module or using the function that we have in FLoRaSat, we have this second part of this section more focused for that kind of user, the developer user. And basically, in that section, we will present the new version of FLoRaSat, the V3 Edu, specifically because this will be the new version. And basically, it doesn't have any sense if they start to work in a previous version because it's more complicated. I mean, it's possible, but it's more complicated. It will require more time. It will require more meetings to understand how works everything in the previous version. But for that, we focus in this second part in the second point of view on the user on the new version of FLoRaSat. Well, as I mentioned before, in the user perspective, we have basically we need to we need to download this branch that we need to load a repository that we have available. It's open to everyone, so you can clone the repo, specifically this branch, FLoRaSat V3. And in that branch, you will have access to the last version of FLoRaSat V2 with all the capabilities available to run any kind of simulation. Well, as I mentioned before, basically you need to set the environment at the moment of install, at the moment of try to run OMNeT++. then we need to open OMNeT++ and install INET. I can show you here how is the process. So I have here OMNeT. Let me. I can show you. Below. So okay. So how? No, how do I hide this? Okay, I think that I can do this. Okay, it's better. For example, if you want to install INET, the INET framework is a very easy process. You need to go health. You need to go to install simulation models. Let me bring this chart because I will show you how how to set and how to configure the files that you want to. And for example, you need to follow and choose. For this moment, we are using the INET 4.3 version, 4.3. So you only need to install it, put a name, and this process will take some minutes. But it's very easy, and it doesn't have any other issue on that. Then you need to run this file, which came in the repo that you clone. You run this file, and you need to pass as parameter the root where you are installing INET. So basically, for this installation, I choose it. I choose the name pod.3, and automatically install INET in that folder. And then you need to run this file, setting.sh, that came with the repo. You need to set two parameters. You need to send two parameters to execute this file. Basically, the installation of INET and then bash to install it in the configure file. After that, well, I show you here how is. I show you here. Well, then you need to, of course, you need to set the project to release, which basically will be only, for example, here. You need to set what is it? Build configuration. You need to set it to release, so it will be very easy. The configuration. Then you need to connect now INET to FLoRaSat. And well, you need to open the project that you cloned. You basically can here open projects from file system, select the folder where you have installed it, when you downloaded FLoRaSat, and then you select it. And after that, you came into the properties of the folder, and you need to set the reference. You need to create the connection of this project with INET. So basically, you go there, and since you installed it before INET, it will appear there all the projects that are open in OMNeT++, and you selected the installation of INET. With that, the only thing that you need to do now is set the source folder as the main project folder of the project. To do this, basically, for this, you need to come to properties of the project. And then you go to here, to this section, and you need to specify the big directory. For this, you can select basically using the workspace, select the project that you're using, and select the source folder. With that in mind, the only thing that you need to do is build the project. Let me show you here. This is building the project. And it will be there will be no problems. And basically, with that in mind, you will have everything to run FLoRaSat. Is everything good? So again, if you at some point you want to try and test it, and if you are having any issues with the installation, just send me a message and I will be happy to help you. Well, following, as I mentioned before, there are the main files that we need to set for this point of view of focus on user. Basically, we need to set, we will talk about more about two files, two kind of files, the net files and the ini files. In the net files, as I mentioned, basically you can describe the structure of the network, describe the structure of this module, how they are connected, how they are. Maybe a module has a submodule in the middle. And basically with the net files, you establish how the components interact between them. And of course, it provides a visual representation of the system of the network. And the other big file that you need to, the big kind of file that you need to set, that you need to work in this when you are a user and you want to test FLoRaSat, basically is the set some ini file. And for this, as I mentioned before, in the ini file you can specify the value of some parameters. You can set the duration of the simulation. You can configure the rules, the initial values, and of course you can define which network you want to use. And basically, if you want to create, if you want to modify something in the simulation, you will basically need to modify this ini file. Basically on that, you need only to select the ini file that you want to run and press the button to run. And that's something that we will do. Just give me a second to put here. Okay, this is the previous version. So for this, I created a simulation case very simple that we can see how we set these parameters and we can understand how these modules interact between them. Here, for example, we have, I think I have here. Yeah. Here we will present three cases, three scenarios. In all the scenarios, we will run a simulation for almost 2,500 seconds. The first packet will be transmitted at the fifth second, and the transmission to the next packet it will vary according to the scenario. For the fifth scenario, we will transmit the next packet at the 5th second. For the other both, we'll transmit each 100 seconds. Additionally, we have another parameter that we can modify if we want. Basically, this parameter will allow us to receive the package in the satellite, ignoring or not ignoring the interference. I mean, in the case of some devices try to transmit to the same satellite, it can create a collision. So modifying this parameter, we can see that there is we can activate or deactivate the detection of collision. And we also have another parameter, which basically is the power of the transmission. We can set them very easily. It's only change a value, and we will see how the results will change. Yes. Yeah. Sorry? No, OMNeT is open source. It's open source. OMNeT is open source. FLoRaSat is open source. Everything is open source. Yeah, I mean, there is a pro version, but we developed FLoRaSat using the open source version. So no, it's not necessary to pay any kind of money for OMNeT. As I mentioned before, basically we will have three scenarios. Here it is. Let me. Okay. Basically, in this scenario, we set the most important part, I think, is set the correct network. And as we can see here, we have a net file that basically in the net file you set the modules that you want to have in your network. Here, for example, we have a ground station module that basically represents a ground station. And as you can see, we can create several ground stations at the same time. And in this case, we are creating a vector of ground stations. Basically, it's a parameter. This number, this parameter number of TS, basically indicates the number of ground stations that we will have, and this parameter you set it in the ini file. And also you have another module, basically is the satellite, which represents the number of satellites that we will have in the sky and in the space. And of course, this there is a constellation creator module where basically you can create, as I mentioned before, you can create a constellation that you will need. And of course, there will be, it's necessary to have, for example, if you have a constellation, if you want to have a constellation, I don't know, maybe a Starlink constellation, you need to set a highest number of satellites. So it needs to be very, the both modules are very synchronized to validate this kind of restrictions. Then the other important module is the LoRa nodes. Basically, it represents the devices in ground, and they represent how they are. That number of devices is almost the same that the ground station. But in this case, as you noted, this is the name of the network. This is routing GS to LN, which is I should change. I need to change it, but basically, in that way, you set the network that you will use for this simulation, and then you need to set the other parameters. I mean, for example, you can set the propagation. You can set the path loss that you will have, and in this case, for example, we have we want to set the duration of the simulation. We need to go here and here. You can find, for example, that this simulation will run for all this duration, and in the case of the time to the first packet of transmission, or also time to the next packet to the transmission, you basically you have here another parameter just to set. What is it? Here you have here the parameter that you set. As you see, basically it's only put the name of the parameter and with the value that you want to put. And in this scenario, the time to first packet is the first second, and each 50 seconds it will transmit a new packet. And additionally, we can see the other module, the other parameter that is ignore interference. It should be here. Well, as you can see, we are setting here the parameter just to see, just to set that this simulation will not ignore the interference. And for example, to set the power of the transmission, we need to go to the section of the LoRa nodes, and here you can set the transmission power to 14 dBm, which is enough to reach from the device to the satellite according to the medium that we set in this case. With that in mind, basically the only thing that we need to do, as I said before, is choose the ini file that you want to do. And for example, another interesting thing is here. What is it? I don't know. If you, for example, you want in this simulation, we will use an Iridium constellation, basically just to avoid that the file be very big. We can set the configuration of the constellation in another file, and as we can see, we have the Iridium parameters here, and here you have all the parameters required for the interplane spacing, the plane count, all the parameters required for the creation of this kind of constellation. Mm-hmm. So yeah. So I didn't hear you well. Maybe. Yeah, no problem. No problem. Yeah. Okay. Oh, okay. I understand. Yeah. 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 Okay. Okay. Understand. But maybe we can talk. Yes. Yes. No. Yeah. Yeah. No problem. Well, continue. Additionally, you have, for example, for the device, you can basically set the number of the device, and for this you set to the latitude and the longitude, the position, the exact position of the device. And well, basically, it's a long file where you can set and you can modify according to your application or your your purpose. And basically, it's only set the number of devices and set the latitude and longitude of all of them. And then it's similar with the ground station. In this case, we have 20 ground stations. It's similar. You need to have the latitude, the longitude, but additionally, you can put some name. You can give an ID to the ground station. Well, it's almost the same process. You set all the parameters for each of them, each of the ground station. Well, with that in mind, the only thing that we can do now is run. Wait, I think I run the run simulation. So let me check here. Yeah, you can define any place you want according to your purpose. Via ground station. I mean, until I know is that the information is kind of it's private. It's configured, and that's uh, for example, that's one of the objectives of FLoRaSat. You are free to set as any place that you want to put a satellite or a transmission. So you can set very easy, and you can execute according to your purpose. No, no, we don't. We don't. At the moment, we are not working with that kind of information. Well, basically, here we execute, and as we can see, we have a constellation satellite, which basically is very good represented. And this is something good about FLoRaSat, because I worked with other kind of simulator, and they are more focused only by code. You cannot see how graphically you cannot see how you put the satellite. You cannot see how they are connected. You cannot see how the packet is transmitted, and this is something that we will see in the simulation. Here, additionally, for example, we have some devices. Sorry, we have some IoT devices which are represented using this node. And I think that you can see better here. Here is a node, IoT device, and what this is basically a satellite. Well, To establish the position, we use the ini files before, and the idea of this is to see how the simulation runs. So if we start play, it will start to initialize all the parameters as we mentioned before in the flow of the event driver simulator, and then it will start to transmit. So for this, as we can see here, we have all this the transmission that we received, but I have an error that this is in yeah, sorry, I choose it another. This should be LoRaWAN. Yeah, it should use the LoRaWAN MAC protocol. So we started again. Sorry of this one. So the process is similar. It will do the same. So what happened in this scenario is we set it in order to, okay, the device transmits to the satellite, but the destination, the final destination is the nearest ground station available. So the process is this. In the device is calculated the route that we follow, because you can set several algorithms, and we define the route on the device, and after that, but that device transmits to all the satellites that are near. So it will, as you saw it before, the device transmits to everyone, and only the satellite that are that is part of the route will be able to retransmit the data to the final destination. So as we can see here, they are moving, and they are going to the final ground station. And what this happened in the first second, and now we need to wait until the next 50 seconds to run it. And as we can see, the satellites are moving. So this is how this is something that I really like about FLoRaSat, because you can see how the constellation are moving. You can see how the nodes, the IoT devices transmit to them, and see actually how the network works, how the network see. And this is, I think, this is very important for cases when you are a student and you don't have you don't know a lot about this field, and you can see very in a very didactic way how they work together. And what now is in the 50 seconds, so it will start to transmit again, and it will do the same. And yeah, basically it's only 2 or 1 satellite maximum, and then it will reach the final ground station. So here, for example, we can run until the end without animation. Very easy, just to have the final files. It will take some time. Well, this is the end of the simulation. We can close it here. And now, since we run the simulation, for example, we have some metrics to see and understand how this model, this network works. For example, in this, here we have, well, this is the file that are generated using this simulation, and here we can see I just put some parameters. For example, number of packets sent. In this case, let me show you. In this way, you can check, for example, some metrics that you need to put in that you want to see. For this presentation, I prepared 2 metrics: the number of packets sent by each device, and the number of packets received. at the final ground station, because it can happen, for example, that there will be collision or something like that. It's not always the same. But for example, here we can set the module if we only want to see the LoRa nodes, and as we can see, all the IoT devices transmit the same number of packets, which basically is very intuitive according to the parameters that we have. Since we will execute each 50 seconds, it's only divide the simulation time according to each execution, and it's very easy to see that all the devices transmit 50 times. However, if we compare it with number of packets received, in this case, we need, since the receiver now is the ground station, we need to set here the ground station. Here we can see that not all the ground stations receive the same number of packets, since the objective of this simulation is transmit from the device to the nearest ground station. According to the distribution that you have, maybe there are some ground stations that is more closer to other ones. So that's why, for example, here I think this ground station has more receive more packets than the others. And for example, we can do this. We can create it. We can copy this. Let me create it. No. Yeah. For example, we can run this. I mean, this is a very, we can do it in a better way, but we can zoom all these parameters that are received, all the packets that are received, and we notice that it's not the same, it's not the same that the packets that are sent, specifically because in this configuration, we set it that, the interference we detected. So there are some cases of collision cases where two devices, I suppose that most in the case of this ground station, where two devices try to transmit to the same satellite, but the satellite is not able to deal with the collision, so it discarded. So that's the reason why in this scenario there is the lower of package is not the package received is lower. However, we also, for example, we can run the other. This is the file where we can see. Well, wait, what is it? Okay. This is the first scenario. Now, if we, for example, we have another scenario, which basically we will follow this configuration, this table of configuration, and the simulation duration is the same. We have also the, for example, time to next packet. If we look the parameter, now it's set to 100. Each 100 seconds, the devices will transmit. And here we have, for example, ignore interference. Here is set to allow collision, basically. And in this case, we are setting a low power of transmission. Where is it? Here. We are setting here a low power transmission, which implies that there will be some cases where the device will transmit to the satellite, but if the satellite is kind of far, it will not be able, the transmission power, it will not be able to reach the satellite. So for this, there will be some cases where the transmission won't be successful. So this is something that we will see in the moment to analyze the metrics of this simulation. Basically, the other configuration is similar. It's the same constellation. It's the same number of devices, the same number of ground stations. And if we came here and we need to we run the simulation. We see the same. Just let me check if I have this. If it's set the correct parameter, the correct path protocol. Okay, it's the same process. All the parameters are set at the beginning, and they started to transmit to the other one, and so on. Now, if we go to until the end of the simulation, and here, for example, in the results folder, we open this is the file that was created with the results of the second simulation. If we open it, it will necessary to create a file to see this. And here, for example, we have almost the same. We have another. We can check the name, the same metrics, number of packets sent. We set it here for LoRa nodes. So, as we see, is this in this opportunity, the number of packets decreased because the time window is bigger now. So now it's 100. So it's obvious that it would be only each device will transmit 25 packets. The important thing here is just to see, for example, the number of packets received. These need to be checked in the ground station. Okay. Well, basically, in this case, since we set it a low power of no sé. Since we set it a low power of transmission power, a lot of packets are not received in the satellite. So that's why here we see that the number of packets received is very low. But for example, in the OMNeT 3, in the other simulation scenario that we have here, we put it the correct energy, the sufficient energy to reach the satellite. And if we run this simulation, we will see that the number of packets received is very bigger if we compare with the second scenario. It's the same. Let me put this here, run until the end. Then close this. Run until. Okay, here. Where is it? Here. And you can check. For example, gross data, colors, and check it number of packets received. Again, in the ground station section. Yeah, if you compare here, there is a big difference between the number of packets received because in this scenario, you have enough power to transmit and reach the satellite. Well, basically, in this section, we presented how to manage, how to set the parameters, and how to execute simulation in FLoRaSat, even how to see some metrics, and how to analyze them. And of course, you can import this data to another file to create more sophisticated graphs, more sophisticated metrics. But now I will talk about this other point of view that I mentioned before. This point of view more focused for developers. Well, in this, for this point of view, basically we will use this new version of FLoRaSat that I mentioned, the FLoRaSat V3. Basically for this. Let me put it bigger. Basically for this. Here in the left image, we can see that this is the representation of satellite models in the previous version. As you can see, there are several modules, there are several gates, several connections, and it's kinda complicated to start to work. It's not friendly user basically, but for that, basically in this version we make a restructure of the architecture, a restructure, a redefinition of the modules, and we try to synthesize and make it best friendly for developers. As we can see in the other image, is a new representation that we have for satellite model. Yeah. In this case, for example, we have a representation of this, the architecture of the new version of FLoRaSat. Basically, we have two main sections. A big one is the global section that basically has each other model has the global section, and here we put some modules that need to be that doesn't have a proper OMNeT. Basically, it's a global section. We have, for example, the medium, the constellation, and the topology concept. And specifically, the constellation creator. In the other section, we have the nodes. That's how we call it. Basically, they represent the three main aspects, the three main elements of this new version of FLoRaSat. We have the terminal and we have satellite, and we have also the station. Each of these nodes has its own submodule that represents, for example, the physical layer, represents the data layer, the network, the application, the energy, and the mobility. In the case of the satellite, in order to make it more valuable for new development and so on, we have also a new we created a specific physical and data link for each kind of connection. For example, the satellite can have three kinds of connection. Basically, we can have a connection between other satellites. Will be the inter-satellite links, and also we have a connection with the ground station. That will be the ground station link, and also we have the connection with the device, which we call it device link, device satellite link, device satellite link. Each of these connections has its own physical and data link layer. And what in global, the satellite, additionally to connection, also has a network module, an application module, an energy and mobility module. And the section basically is the same. We have the same module, but the important thing of this is that we synthesize everything, we reduce the complexity, and we give it a new approach, more friendly for the developer, more friendly for new users, for new students that want to participate, or maybe some create some modules. This architecture is not extensible for new developers. Well, in this case, also the process is the same. You can upload each repo that is available. It's that branch, and well, in this case, it's not necessary to set the source folder. It's only load the repo and execute it. And we will see here how is the repo projected. Let me close here just to make it more. This is FLoRaSat P3 Edu. And here, as you see, I mean, we didn't migrate everything from the previous version to this new one. So that's the reason why, for example, in this new version, we only have the satellite, well, we have the main component, but we don't have the routing algorithm. We don't have all the capabilities that we had in the previous version, because this is something that it will require some time. But we really think that this is a critical step just to keep improving the potential of FLoRaSat. As you can see here, basically you have For example, in the previous FLoRaSat, in the previous FLoRaSat, you have all these folders, which is kind of complicated to understand. And for this, we reduce it in this new version. We reduce it very simple. Just we have, as we presented in the architecture, you have the global section that is accessible for all the modules, and you also have, for example, the nodes. This is the most important part because it represents how easy it is now to work and understand FLoRaSat. For example, you have the terminals that basically represent the device, the IoT device. You have the satellite that, of course, represents the satellite, the station that represents the ground station. And as I mentioned it before, each of these folders has its own subfolder. For example, here we have the physical, the data link layer, the network layer, the application, the energy, and the mobility. And each of these has the implementation required for that section of the node. Basically, is something that I think they have something here. Here we can see an overview of the architecture. It's just MD file, just to see how is this set it and how is it configured. Each node is organized by the OSI layers, and satellites, as I mentioned it before, is split in DSL, GSL, and ISL connections. And each of these modules has its own implementation of physical and data link layer. And the global directory contains the logic for medium, message, mobility, utilities, and the rest of the components required. Okay, so in this case, for example, we also have a simulation that we set it. Okay. In this case, it's similar. It's kind of similar. You need to set, for example, the medium, specify the name medium. Now we changed the name of LoRa nodes. We changed it to terminal. Basically, you need to set the number of terminals similar. Now also you need to have set the satellites, the number of satellites. We also have some. We migrated the constellation creator, so you will be able to create a constellation in this new version of in this new version of FLoRaSat. And you also need to set the ground station that we call it in this new version station, and everything. Well, let me run the simulation. As used, the main configuration is almost similar. For example, you need to set the constellation that you want to create, a Iridium constellation with 66 satellites. You need to set another parameters, but as you see, it's more clean, it's more easy to the configuration of this ini file. And the only thing that you need to, according to the feature that we have now in this new version of, is kind of easy, the process of execution. And now, since this is a point of view more focused for developers, if you, I can show, for example, how the connections, how the modules are connected, how the net files are connected. For example, here, this is basically the representation, the net file of the terminal that we use. And as you can see, there are some parameters. There is also the gate, and there is these two modules that we use, which basically represent the same modules that we presented in the architecture. Here we have the physical layer, the terminal data link layer, the transmission, the network layer, the application, the energy, and the mobility. And for example, if you go here to the mobility, you can see the representation of that model. Here also the mobility is of the terminal basically is a net file, and in this file you set the parameters required for this kind of model. No? Since this model represents the mobility is focused on on a terminal on a IoT device, you basically need to set the latitude, the longitude, the radius of transmission, and other external parameters that is required for the initialization of the terminal. With this in mind, basically the only thing that you need to do here is create an instance of this module, and that module will represent the mobility of the device. Here down we set the connections of the required for this module. And if we see here, for example, is a easy and very friendly representation of this module. We have each of these section that represent the physical, the data link layer, the network layer, and the application. And of course, there also exists this energy and mobility model. Another interesting model that we have here, for example, will be the satellite. As you can see, it's very easy and very friendly. Yep. In the satellite, you also have some submodules that, as I mentioned before, as I presented before in the architecture, you have for each kind of connection, DSL, GSL, or ISL, you have your own physical and data link layer. So that's why, for example, if you go here to the satellite physical layer, you go to the declaration, you can see that there is the radio for that DSL. I mean, this is the radio that we use for the connection from the device to the satellite. But, however, if, for example, we go for another, all this is focused for the DSL, right? You go to the other section, for example, to the mobility. This represents the mobility of all the satellite without specifying the connection, the kind of connection that you will have. And it's well, in this case, again, if you see this new representation, it's kind of simple, it's kind of friendly user, so it's not a mess like it used to be. So here we can test this simulation. Okay, here as you can see, it's similar. The constellation is created with the satellites using the parameter set at the beginning. You also have that ground station, and you also have the IoT devices dispersed around the world. In this case, we will use, and that's something that we presented in this slide. Sorry, let me put this. For example, here we presented a MAC classification of the MAC protocols that exist. Of course, the most common is the contention free MAC protocols that when we see in the image we have FDN, CDN, CDN, but we also have, for example, some contention based random access protocols. That, as we can see, we have an loaded and offloaded array. The most important is here that in this image we see, for example, how this, which companies are using this kind of model. For example, we see that IMEI works specifically with contention-based random access protocol, and this is something that we, for example, that we present. In this new version of FLoRaSat, I mean, we will move everything, all the models that we have in the previous version, but now, for the moment, we moved this TMAC protocol that we developed previously and presented in some paper. Well, basically, this TMAC protocol is a MAC protocol focused on repetition. So, with this in mind, this protocol tries to reduce and increase the probability of try to increase of the at the ground station, because basically the device transmits one time and then tries to transmit again the same packet, and it also considers, for example, the problems of visibility. If one satellite is moving and at some point I will not able to reach, I will try to send the same packet some seconds later, and hope that the package, the satellite is close to me, so I can reach the packet. So basically, with that in mind, for this parameter, for this mesh protocol, we have four parameters that we need to set. For example, we have the time to start the transmission. Basically, the time where to start the first transmission. And of course, you also have this window of transmission, and the other parameter represents the time between the next transmission. For example, if you have a window of 100 seconds, you in that window you need to transmit several times. That is also a parameter that you set. And for example, if you say in this window transmission, I will transmit each 20 seconds, so that represents that parameter. That's the time between the transmission. Then next, you have the time to the next message, and also the most important parameter is the number of repetitions. So basically, since this is a protocol focused on repetitions, this parameter represents how many times I will transmit. I will try to transmit the same packet. Basically, with that in mind, we need to the objective of this kind of protocol is try to address the problems of the intermittent visibility of the satellite, or any kind of problem that could happen between the transmission. For that, with that in mind, here, and this can be very interesting because we can see how the MAC protocol works in this new version of FLoRaSat. Basically, we need to go to the data link, and here, just to understand the process to go deeper. For example, here we have the submodules of the terminal, and we go to the data link layer, which is the place where the MAC is in, and we go to the declaration. And sorry, what is it? Yeah. Here, there is some comments, but basically we set the Key1 node MAC. So we said that we are using this new MAC that we call it TMAC, or what it happens that here it has the name of Key1. So here, if we go to this file, basically we have this representation of the parameter. As you can see, for example, you have the parameters that we presented in the previous slide, with just an initialization. You also have, it would be better if we see. Yeah. You also you see here, for example, the Key1 node MAC, that is the name that we said it before. You see all the parameters that are required for this MAC protocol, and of course there is you can set a value default for value. Okay, and then you also have some LoRa parameters required for the transmission. And basically in that you can see here the implementation of this MAC protocol. First, you read the parameters of the protocol, and they are set it in you can set it in the ini file, or you can use the default values that you took from the net file. The main function will be here. For example, you need to where is it? Yeah. For example, in this MAC protocol, we have two states. We have the state of transmit, which represents that the device is transmitting in this time. And we also have the other state that represents that the device is waiting, idle time. And when the device is in the idle time, basically what we need to do is schedule the next transmission. And if the device is in the transmit state, we need to create, it depends in which state of the simulation we are. For example, if we go to the scheduled transmission, here, basically the only thing that you can do is you schedule an event in this just in this moment, and this event will and which will message you transmit in this new transmission. Here you said that for this transmission you will send this message. Basically, this is how you start to set and develop this logic. You see that you use the parameters that you set in the net file, maybe or in the ini file, and then you use those parameters and try to represent the best logic that you want to create. For this specific MAC protocol, we have this logic that basically represents transmit each time several times the number until you reach the number of repetition. Here we have Q1 transmit. For example, if you see, we have this. When we want to schedule a transmission, we are sending this message, event start transmission, and of course we change the state to Q1 transmit. So when the module start to process this new event, and according to we are sending this message, basically we will come to this section, and this section will create the transmission windows and see how if reach or not the number of transmission set at the beginning. And at the end, if we go to this function, basically is the function that transmits the packet to the next layer of the application. Since we are here in the data layer, this will transmit to the physical layer to be transmitted. So, for example, if we execute the test global simulation. Oh, wait, I think I have it. Yeah. So in this case, the transmission will occur not on all devices at the same time. It will occur according to the parameters that we set it, and according to the number of repetitions. For example, in this case, first they are initializing the modules, and in this case, the first device that transmit was this one. And this scenario is configured just to transmit from the device to the satellite, and the satellite will transmit to the first ground station that he found. So we see, for example, again, we see here, if we execute, it's initialization phase. The device transmit to both satellites, and both satellites transmit to the first ground station that they see. And this is, but in this case, only the transmission is not for all the devices. It's only for some specific devices. If we keep running the simulation, we see that there is another device, and it's the same. It's transmit to the first ground station that it found. If it founds, maybe it doesn't found. maybe the satellite is not connected to a ground station. So if that happens, for the moment, it's discarding the message. But we can create, for example, a queue just to store the package until they found a connection to other ground station. And so on. With that in mind, basically, in this new version of FLoRaSat, we were able to migrate that constellation creator. We were able to migrate the most critical, the core components of the of to create a transmission. I mean, the physical layer of devices, of satellite, and the ground station. We were able to create a MAC protocol in the terminal. And well, we have a lot of work yet to do. For example, we didn't migrate yet the routing sandbox that we have. And so for the moment, that's the reason why for the moment the satellites only receive the message and transmit to the field ground station that they found. But in the previous simulation, for example, you see that the satellite transmits to other satellite because it follows a routing that it was set at the beginning. So, but now, since we are in the process of migration, we only move the core components and we are going to keep moving the other one. No? But now, with this new version, we really think that this is critical because FLoRaSat was growing so fast, and it was necessary to have to set a breaking point and start a refactory of the process. Well, basically that's almost all my presentation for today. Just let me finish, please, the presentation. Well, as I mentioned before, DTS IoT plays a key role in extending the IoT application that we have had in the future. And of course, this is critical for remote areas or like like the desert, the sea, the ocean, where the implementation of a terrestrial gateway is not feasible, is not possible, is not economical viable. So that's is a critical actor for this kind of application of this kind of scenario. And of course, OMNeT with Ylnner and FLoRa, those are the frameworks that we use. All these technologies we use to create FLoRaSat. And of course, FLoRaSat, and we demonstrated in this presentation and we demonstrated in the previous publication, it's an end-to-end simulator timer for DTS IoT scenario that supports both point of view researchers and developers, users, any kind of profile can try to use FLoRaSat, and it's a process very easy. More in the architecture if you have a developer, and also it's very easy if you have only a user that wants to set some parameters and see how the network works. It's also a very important tool to use, to have in consideration. Well, the user perspective of this tutorial explaining how to set, how to execute, how to see the metrics that we define in the simulation, and the developer point of view demonstrate how to work and how to develop it on this new version of FLoRaSat, which is as I mentioned, the new version of FLoRaSat is under development. And basically, the idea of this new version is be more intuitive, be more friendly for new users. It can be researchers, students, it can be professionals, any kind of user. And of course, we are doing that with objective to improve the usability and understanding of this kind of tools. Well, with all this in mind, FLoRaSat provides a didactic research platform to experimentation for DTS IoT network, DTS IoT solutions. Well, I want to finish this presentation with another section, specifically with the European Union Horizon Research and Innovation Program, which basically supports my PhD. And also I want to say thanks to the alternative version, which is they were basically the main they motivated us to prepare this presentation. Well, special thanks to all the participants of this tutorial, and I hope that you like it. And if you are again, if you're interested to start to work on FLoRaSat or even OMNeT, you have any problem with that, you can send us a message to me or talk later. Just feel free to talk. That will be all. I don't know if you have any question or you want to. We can also have Juan and Benoit, they can participate. If you have a specific question, they can also participate. Yep. Yeah. The new version? Yeah, the new version of FLoRaSat. Yes, I mean, we try to rush for this presentation the migration, so in order to present and introduce this new architecture. But Benoit and I were working really having tried to actually we are very motivated in this new architecture of FLoRaSat, and we hope that it won't take any it won't necessarily enough a lot of time to have a standard version of IoT. I don't know specifically. I cannot give you a specific date, but we are working really hard in this new version, and I think that the idea is to start to migrate the main modules that we made it now, and start to migrate as according to our necessities, according to our purpose, and see how is the process? I mean, if someone wants to participate or wants to, and the student wants to participate or be involved in FLoRaSat, I think this is the best moment because it's a new architecture and big part of this new process. It will give you knowledge of the previous architecture, just the necessary knowledge, and you will, and we will can work together with me, Juan, Benoit, and participate and be. And the objective is to have this new version of FLoRaSat as soon as possible.
Debilitation, feeling alive. Like a comet racing through the sky. Under neon skies.